CH2, then CH, I will make CH3, CH2 plus. This is a primary. Then you have CH3, CH, and again you have CH3 on this side, not H. This is secondary. Then you have CH3, then you have CH3, CH3 plus. So we should denote it like like this: 1 degree, that is primary; 2 degree, 3 degree is a tertiary. So tertiary carbocation is the most stable because 3 alkyl donating groups, okay, are doing what? They are neutralizing the positive charge of the carbocation, okay, because they are donating, trying to donate electrons are negative, so we have to make it neutralize the positive charge. So three groups are trying to neutralize, okay. In primary only one group is trying, in secondary only two groups are trying. So I'll just write it. Is more stable because three alkyl groups are inducing negative charge for neutralizing positive charge of carbocation. Okay, so what does this whole concept has to do with the Markovnikov's rule? So when an electrophile is bonded, okay, in such a way that tertiary carbocation is produced. So this can only happen if the hydrogen attached itself with the carbon with most hydrogen, uh, like this. When we did the example above, what we actually made here, the major product was a secondary. Okay, this is a secondary halogen alkene because it has chlorine on the the carbon which has chlorine attached to it only has one hydrogen. It is a secondary. Okay, so basically this was a secondary carbocation. This was a primary carbocation. So primary is less stable, secondary is more stable. That is why we always attach the hydrogen to the one that already had more hydrogens, so that the it tries to make a tertiary carbocation, or it tries to make a secondary carbocation which is more stable. Okay, basically you just have to make the intermediate that is more stable, so that the coming electrophile then attached to that secondary, tertiary, okay, carbocation. So basically we avoid to make the primary carbocation. Clear? So this was the whole the mechanism of electrophilic addition, how the Markovnikov's rule apply here. Now we're just going to see the some reactions, okay, that all are basically sort of doing electrophilic addition. The mechanism, okay. Previously, I told you about the type of reaction, name of mechanism difference. Now we're going to doing the type of reaction, okay, the general name of reaction. But behind the scenes, behind this mechanism, what is happening actually? Electrophilic addition is happening. So some reactions. First is quite simple. What we are doing later, we are doing hydrogenation. That is adding hydrogen, electrophilic addition of hydrogen. Um, Reagents, I'll just write here. Reagent, condition, and what else we have? Yeah, reagent is hydrogen gas. Okay. Conditions are a nickel catalyst. Okay, heat at 150 degree Celsius with nickel catalyst. Hydrogen, hydrogen, then you have hydrogen, then you have hydrogen plus H2, arrow, C double bond. Okay, now you just have to know that the hydrogens are attached here. Okay, moving on to the second one. That is addition of steam, that is hydration. Okay, for hydration you have reagent conditions again. Reagent you have steam, that is water but in the gaseous form. And apart from that you have temperature 330 degree, 60 atm atmospheric pressure, and you have catalyst 300-degree temperature, 60 atmospheric pressure, and phosphoric acid as the catalyst. So the equation is quite simple. Like if you are trying to add CH2 and then water, it will make CH3 CH2 OH. Now what you have made, you have actually made an alcohol with it. Okay, that we'll study in the later chapters. So in this reaction, Markovni-Cox rules will be applied. Okay, in the bigger chains. So Next is addition of halogen, that we call it as halogenation. Halogenation, that you are adding an halogen with it. For that you again have region conditions. Regions will be an halogen. Okay, it will be halogen, which means group 2 elements. Okay, X I just written in general. Okay, this is dissolved in CCl4 tetrachloromethane. Okay, because tetrachloromethane is a solvent that we will use in the organic section. Okay, in inorganic, we usually use water to dissolve something as a solvent, but in organic we use CCl4. It is the solvent of the organic section. Clear? Then you have this the it can be done, this reaction can easily be done in RTP in dark. Like if I take an unsymmetrical alkene, sorry, so and I need to add HCl with it, sorry, Cl2 with it. Okay, I will just take a bromine. Okay, this time we have already taken Cl a lot of times. Br2. So it will be like CH3, CH, Br, and CH2, Br. Okay, you don't have to add the bracket in the end one. It's just an optional. What will be the name of this compound? Can you name it? Are you able to name it? Uh, it will be one, yeah, dibromo, yeah. Okay, good. So this will be the action. Okay, now what as we are doing here is okay, you should be able try to practice at home all the electrophilic mechanisms of these the reactions we are doing. Okay, any of these reaction can come and you just have to draw the electrophilic addition mechanism of that. Okay, so what is the observation of this reaction? The observation is that just for this reaction, okay, if we had added chlorine, then there would not have been such an observation, but bromine is of brown color. So if you're bonding the bromine with organic alkene, so bromine water is of orange color basically, or you can say brown color. So brown color of bromine water is decolorized. That is basically the reaction. Okay, apart from this, if we ethene if bubbled, okay, this is again the reaction of this only. When ethene is bubbled in aqueous, okay, Br2, then what will be the reaction? CH2, CH2. Now this is an aqueous bromine, okay, and we are now trying to bubble it through the water. So the water is not going to dissolve with the bromine. Instead, it will react again with whom? Ethene. So basically you will be getting two type of products. You will be getting two bromines on both side, and you will be getting another ethene molecule which will have one bromine and one OH attached to it. And the last, the hydrogen was left, okay, of the water, that will react with one Br that was there. So this is one sort of reaction that can happen, and it usually happens at room temperature. Okay, clear? Then you have addition of hydrogen halides. For hydrogen halides, what we can write here is that one is also quite easy. You just have to done this at room temperature. We already drawn the mechanism also. This is our fourth. I'll just draw one equation, okay, that is quite simple. HBr, okay, if you are taking HBr. So the thing to focus on is by the use of Markovnikov's rule. So the Br will be added on the hydrogen with less carbons and hydrogen with more, okay, carbon with more hydrogens already. And okay, no byproduct is not there, and this is done at room temperature and pressure, RTP. Okay, apart from this, what is left? Let me see. Okay, now coming on to the reaction that is not electrophilic addition. It could be electrophilic addition, but the type of reaction that is being done here is oxidation. So you have two type of oxidations. Okay, two cases oxidation of alkenes. First one is by cold. I would write it like cold and dilute KMNO4, potassium magnate. Because potassium, why we are using potassium? Because we need to do oxidation and we need some oxidizing agent. Okay, basically you are trying to add oxygen in alkenes. So what happens? This is done at room temperature and pressure, but the products that is formed, bracket and then oxygen within it. What does this show? That this oxygen is coming from this KMnO4. Okay, because we do not write the whole equations in this. That would be much more complex. So we are just writing that this oxygen has came from this oxidizing agent, and also you have to add some water in it because you have added dilute solution. The dilute means there's so much water in it. What happens? CH2 single bond CH2, OH added here and OH added here. You have made a diol here. Diols are that have two OH functional groups with them. And what do we have to? It will be a RTP. Okay, the conditions are basically the one that I've already written here. Okay, cold dilute KMnO4. That is basically your condition. That is basically your conditions. And what are the reagent? Reagent is a KMnO4. Clear? And what we have actually made from ethene, we have made, how do we pronounce it? We call it ethane, okay, diol, or you can say ethane 1,2 diol. Ethane 1,2 diol. That is the name of this compound. So this reaction is quite easy. You just have to add OH on the two carbons which were bonded together by the double bond. Okay, now this is another test, sort of a test that you can use to differentiate between alkane and alkenes. Okay, because only alkenes will react like this. So again we have an observation here. You should remember the observations. Observation is that KMnO4 is of purple color. Okay, so when it reacts with ethene, it decolorizes and becomes colorless. So I'll just write color of solution, because when you are adding, the color will be, color changes from purple to colorless. Okay, or I'll just say solution changes from purple to colorless. So we noted down two tests to distinguish alkenes and alkanes. One was and two was. So one was that addition of Br2, bromine water. Okay, and the second one is oxidation by cold dilute KMnO4. So okay, so you should remember both the test and their observations. Clear? um okay, for the second one, now I'm changing the conditions. I'm changing, the reagent is same, the conditions are being changed, which means now I am doing the oxidation. Again we are doing the oxidation, but this time we are using hot instead of cold, and we are using concentrated instead of dilute KMnO4. Now what will happen? So now you need to look into some things. Okay, now you are using, sort of very powerful conditions. You are using powerful conditions. Okay, we should also write here acidified KMnO4. Okay, I'm also acidifying the KMnO4. Why we are doing that, we'll look into that. KMnO4 acidified. Okay, so you are using very powerful conditions here. So what usually happens, the carbon double bond in the alkene, that breaks down, that comes into the half. Okay, breaks down into half. So we call it as ruptures. Okay, the alkene carbon double bond ruptures, which means breakdowns. So what usually happens, if I am okay, now it basically, what will be the products? Okay, basically you are adding now oxygen. So oxidation will add oxygens in the alkene. So first scenario, if you have carbon double bond, and each carbon, again now you just have to see how many hydrogens are attached to that carbon. This time I'm not attaching any hydrogen with both. Okay, carbons. So both have sort of alkyl chains on both sides. So they do not have any hydrogen with them. So what usually happens here is, when you oxidize it with using these conditions, this bond gets broken down. Okay, it comes into half, and now you try to look. Okay, if this carbon, okay, look into the both carbons. If these carbons do not have any hydrogen attached with them, then only you just have to do what? You just have to make the double bond like this, the half double bond, and again CH3, and you just have to make an O here, oxygen. You just have to attach the oxygen with that double bond. Same thing happened with that carbon. You just have to do this. You just have to attach the oxygen, because I'll explain that in the second concept. So basically, now what you have formed a ketone here. Both are ketones. Okay, I'll just give you a concept of aldehyde and ketones here. Aldehydes are the one that have carbon double bond, but they have H attached to it on the other side. Okay, they have carbon double bond O, and then hydrogen is always there at the end. But ketones are the one that do not have any hydrogens attached to it. Okay, so always if you have two alkyl groups attached to the carbon, you will always be forming a ketone there. Clear? Okay, should I move to the next concept? Now, what if I attach one hydrogen? Okay, same molecule, but now I will attach one hydrogen here. And this will be same with the two alkyls on each end. Now what happens? Now if you try to oxidize this, again the bond is broken down, the bond ruptures. This time again, just draw the similar concept, okay? H here, and you have ketone there. Okay, now what we have done here, we have made one aldehyde and one ketone here. Okay, but this time what happens, the aldehyde is further oxidized. Okay, because you are using so much powerful conditions that what happens, this aldehyde that you have formed further oxidizes to carboxylic acid. Okay, this is one of the reaction of aldehydes, that aldehydes get oxidized to carboxylic acids. So what usually happens here, that this further oxidized and it becomes a carboxylic acid. So it is like CH3 C double bond O, and this becomes the OH, which means O is added here. So aldehyde got oxidized and the ketone do not get oxidized. What is the reason? Because aldehyde has hydrogen with it. Ketone did not have any hydrogen with it, where you would have placed the O. Okay, that is why aldehyde becomes a carboxylic acid and ketone remains ketone. They cannot be further oxidized. Is it clear? So this was two carbons, so it how do we name it? Ethanol, and this is ethanone, and then you oxidized it and made ethanoic acid. That is the whole concept of using hot concentrated acidified KMnO4. Okay, what happens now? Another scenario, the third scenario is the last scenario, that if there were two hydrogens on one carbon, now what will happen? So always remember, if there are two hydrogens, which means two hydrogens are always when the carbon is at the end of the chain. Okay, in this scenario we are doing very smaller chains, but in MCQs you will be looking to very big chains. But always remember, when only that carbon has two hydrogens with it, which has which is at the end of the chain. Okay, at the first or at the end of the chain. So what happens, that this breaks down into, again this bond will be broken down, but this time this CH2 will be converted into carbon dioxide and water. and the other one will be oxidized according to our previous two conditions. If it had one H, if it had two no H, so it will form a ketone. Okay, in this time it will be forming a ketone. So now we have made carbon dioxide and water here. Okay, is it clear? Now one more thing that is left of alkenes concept, that is addition polymerization. Okay, we'll just cover it. It's a quite easy topic, small topic. So addition polymerization, basically we are trying to make a polymer. Polymers are sort of, if we look into closely, long chain of molecules that are made by the repeating units. Okay, and the repeating units we call them as a monomers. So polymer, I'll just write the definition here. A long chain monomers. So now let's just look into and how do they make the polymers, by the carbon double bond joining. Okay, so if I try to draw a polymer known as polypropene, so polypropene is formed when you are trying to attach the monomers of propene together. Okay, so what usually happens is like, now you need only the carbon double bonds. Okay, the rest will be attached like this. You can make it like this, and you have one carbon more, so CH3 can be attached here, and this is your. So what usually happens that we attach the carbon chains like this. You have to repeat the units. CH3, then H. Okay, then again you have on the other side here like H, CH3, H, and so on. The cycle goes on. I'll just make a bracket and N, where N is, you know, a sort of and okay, we usually don't make the brackets in this one. I'll just extend the chain. Okay, I just added the bonds on the either sides, okay, both sides, to show that this is a long chain. To show the sort of repeating unit, you can also make it like this, that show the monomer, like this, and show the bonds, extend them, and keep it n here. N is what? The number of molecules, okay, that are attached, the number of monomers that will be attached here. Apart from this, you have many more like polyethene and other sort of as well. But the main thing that usually comes is the how to draw it, as well as try to figure out the sort of repeating unit in the MCQs. That will solve the question, then you'll get more idea of it. Okay. So now we have completed alkenes. Let's look into some of the past papers of it. Okay, question number 11. Okay, what could be the answer?